This is Ms. White, and in our last bonding video, we will look at intermolecular forces and then bond energy and bond length. Let's look at the difference between inter and intramolecular forces. Intramolecular forces are bonds. They are the forces within a molecule or formula unit. So electrostatic ion-ion forces hold ions together in an ionic bond, and covalent bonds with shared electrons hold atoms together in a covalent compound. Intermolecular forces, or IMFs, are attractions between different molecules. There are three intermolecular forces: London dispersion forces, which are the weakest, dipole-dipole forces, and finally hydrogen bonding, which are the strongest. Hydrogen bonding is not actually a bond, it is an intermolecular force. The chart gives us an idea of the strength of intermolecular forces versus intramolecular forces, which are bonds. So we start with the weakest over here, our London dispersion forces, and then dipole-dipole attractions a little stronger, hydrogen bonding being the strongest intermolecular force, and then we move to intramolecular forces, which are bonds, and we have covalent bonds followed by ionic bonds, which are the strongest. A few facts about intermolecular forces. The boiling point of a liquid is a good measure of the intermolecular forces between molecules. The higher the boiling point, the stronger the forces between molecules. The larger the mass of a molecule and the stronger the IMFs. The more polar the molecule, the stronger the IMFs also, and the more likely it is a liquid or solid at room temperature. Changes in phase of matter, like water boiling or ice melting, are due to changes in intermolecular forces, not intramolecular bonds. The three pictures show our three intermolecular forces. Here we have a hydrogen bond between two water molecules. We have a dipole-dipole attraction between two polar HCl molecules. And we have London dispersion forces between two non-polar chlorine molecules. So let's look first at dipole-dipole forces. Polar molecules with permanent dipoles are attracted to each other. This is because the negative end of one molecule will be attracted to the positive end of the other molecule, approximately 10% as strong as covalent bonds, and the molecules orient themselves to minimize repulsion and actually maximize attractions for each other. The attraction increases with increase in polarity of the molecule. So the more polar the molecule, the stronger the dipole-dipole attraction. And there are some examples: HCl, CHCl3, PH3, all these are polar molecules. Here we can see that the negative end of one HCl molecule is being attracted to the positive end of another HCl molecule, and that creates the dipole-dipole attraction because opposite poles attract. Second type of intermolecular force is the hydrogen bond. This is the strongest intermolecular force. It is actually a type of dipole-dipole attraction, and it is an unusually strong one between molecules where hydrogen atoms are covalently bonded to fluorine, oxygen, or nitrogen only. Notice that these three atoms are the three most electronegative elements on the periodic table. So there are two reasons for the strength of hydrogen bonds. One is the small size of the hydrogen atom, which allows for close attraction in small spaces, because the small hydrogen atom can fit into small spaces. Then it is the large polarity across the molecule due to the very strongly electronegative nature of fluorine, oxygen, and nitrogen. Substances with hydrogen bonding have high boiling points in comparison to similar substances. Hydrogen bonding also accounts for many of water's unique properties. Some examples of molecules which can undergo hydrogen bonding are water, ammonia, hydrogen fluoride, and then if we have an NH end to any molecule or an OH end to any molecule, that could also undergo hydrogen bonding. This picture shows hydrogen bonding between water molecules, and we can see that the negative side of one water molecule again is attracted to the positive side of another molecule, and that creates the force of attraction called hydrogen bonding between the two water molecules. Finally, we have London dispersion forces. Even noble gas atoms and molecules that are not polar will experience weak intermolecular attraction. In any atom or molecule, polar or nonpolar, electrons are in continuous motion. So as a result, at any instant, the electron distribution becomes uneven. This momentary uneven charge creates a temporary positive pole in one part of the atom and a temporary negative pole in another part, and that creates what is called a temporary dipole. The intermolecular attractions resulting from the constant motion of electrons and the creation of those temporary dipoles are called London dispersion forces. So in the picture, we can see a nonpolar chlorine molecule and another nonpolar chlorine molecule, and there are London dispersion forces that attracts the molecules together. A few more things about London dispersion forces. They act between all atoms and molecules, but they are negligible when other IMFs are present. So if there is a dipole-dipole or a hydrogen bond between two molecules, the London dispersion forces are negligible and basically do not account for the attraction between the molecules. They are the only IMFs that are acting among noble gas atoms and nonpolar molecules. They are the weakest of the IMFs, and because London dispersion forces are dependent on the motion of electrons, their strength increases with the number of electrons. So increasing atomic or molar mass will mean stronger London dispersion forces. So the bigger the molecule, the larger the London dispersion forces. Some examples of nonpolar molecules will be methane, oxygen, and nitrogen, and the noble gases, such as helium. Let's look at bond energy and bond length. Remember that atoms bond to become more stable and to reduce their potential energy. So atoms in a bond will maintain a distance of lowest potential energy between them. The potential energy is based on the position of each object, and this is where the forces of attraction and repulsion between atoms is balanced, and we can see that in this picture. So in the chart down here, we can see that a bond will form when atoms are at a certain distance from each other. Over here, the bond hasn't formed. The atoms are separated from each other. They are at high potential energy. As they move closer together, they reduce their potential energy until they form the bond at the lowest possible potential energy. When they get too close together, they become unstable again, and their potential energy increases. So low potential energy means high stability. Bond energy is the energy required to break a chemical bond and form neutral atoms. It is reported for breaking 1 mole of bonds in isolated molecules in the gaseous state, and it is reported in kilojoules per mole. That's the unit. Let's take a look at the relationship between bond length and bond energy. If we look at this chart and we are comparing a single carbon-carbon bond, a double bond, and a triple bond, we can see that the average bond length is shortest in a triple bond and longest in a single bond. Looking at the bond energy, it requires a lot more energy to break a triple bond than it does to break a single bond. Double bonds have 1 sigma and 1 pi bond, so they have to be stronger and shorter than single bonds, which only have 1 sigma bond. And then a triple bond has 1 sigma and 2 pi bonds, so it will be even stronger and shorter than either a single or double bond. So let's picture this. If we have a single bond compared to a double bond, and finally a triple bond, between the 2 carbon atoms, we have a pair of electrons forming that single bond. So the electrons will attract the positive nuclei of those two carbon atoms, pulling them towards each other and forming the bond. If we have a double bond, we have 4 electrons in between the two carbon atoms, so there is more attraction for the two carbon atom nuclei, and they can get closer together, so a double bond will be shorter. In a triple bond, we have 6 electrons in between the two carbon atoms, so this attraction will be even stronger, and the triple bond will be the shortest. As far as the amount of energy required to break the bond, because the attraction is strongest for a triple bond, it will require more energy to break a triple bond, and the attraction is the least for a single bond, so it will require less energy to break a single bond. This concludes our last video. Please come to class prepared with your notes.